Good afternoon, everyone. The work I'm presenting here today, I do on behalf of my co-authors, which are all from either the University of Oldenburg or OFFIS Institute of Information Technology, both located in Oldenburg, Germany. And for the introduction, I would like to take a look at the human visual perception. We just saw it in the last talk, so thank you very much for that preparation here. So our human visual system has a field of view which is larger than 180 degrees, which is quite impressive, but still not 360 degrees. And this is a problem in situations where we want to perceive spatial information about objects that are not within this field of view. And especially, we just saw that when we talk about AR or also VR devices, the field of view of current devices is limited. So it's amplifying the problem of objects going out of view and not be in our field of view, so that we cannot perceive any spatial information about them. There are different situations where this applies. I just searched for some that are fitting for VR. I think the most prominent one is gaming. So just imagine playing a spaceship game for Elite Dangerous here, where you control your own spaceship and you have to fight off some opponents that are around you and you don't know where they are. So there it would be helpful to get some spatial cues. But also in farther in the future, if we think of remote scenarios in VR, where we take over, for example, with takeover requests for autonomous vehicles, when we take over control of drones, for example, in a search and rescue mission, where we have a couple of those and want to know where they are around us. In previous work, we already introduced a visualization technique called IC360. Which allows us to understand in which direction and which distance multiple out-of-view objects are. Here, the objects are shown on a 2D radar in front of the user. And the direction to the object is encoded with the 2D position on that radar. And the distance to the object is encoded with color from red to blue. So red means an object is really close. And blue means an object is farther away. More recently, last year on ISMAR, Borg et al. Looked at 6 different techniques in AR for visual guidance towards out-of-view objects. And they figured out that IC360 performs quite well for a search time. So IC360 was the fastest algorithm visualization technique for locating these objects. And also had the highest usability and lowest workload. Second here was another technique that is called 3D radar, which can be seen on the third picture in the top row. The technique here is a little bit different. For 3D radar, it's an overview+detail approach. That means we have our detailed view and see an overview of the scene. And in this 3D radar, the objects are rendered, but also we have to find ourselves in that radar, so where we are. While IC360 is slightly better there because it's a Focus+context approach, which means information is presented along the borders of the screen and is in line with our current egocentric perspective. So we don't have to switch between our own egocentric perspective and the exocentric perspective of the visualization technique. Now we could say work is done, everything is fine, but the problem is all these visualization techniques, and these were just some examples, previously just looked into static objects, which are typical scenarios where you wear a HoloLens, for example, and you have a couple of holograms around you. They stay at their position and you want to know where they are. That's very simple, but it gets a little bit more complicated when these objects can also move around in the scene. And therefore, we did a user study here where we compared both approaches, like the overview+detail approach represented by 3D radar, and the Focus+context approach represented by IC360. We implemented both techniques in Unity and deployed them on the HTC Vive. Our user study was then looking into movement estimation error, so like how well can people perceive the movement of these objects out of view. We compared the both the techniques, IC360 and 3D radar, and we compared 3 types of movement: linear, distance, and orbital movement. I will say a little bit more about that on the next slide. Then we were assessing like how well people perceived that movement. So with a movement estimation error, which basically means so like the movement was like drawn out of view and the user had to assess that movement, and we compared like these both vectors and like calculated the error as the angular error between these 2 vectors. Further, we also used a system usability scale, and we had a subjective questionnaire. These are all investigated types of movement in our user studies. We had the linear movement, which is like a movement from any point A to any point B around the user. Then we had a specific type of movement, which was called the distance movement here, which was a movement that was either going towards the user or away from the user, also in a linear movement. And we had an orbital movement where objects were not moving any closer or far away, but were just changing the direction in which they appeared. Our procedure was that we gave first like an introduction to the HTC Vive, and then we tested each technique in 1 block. Both blocks were counterbalanced, and we tested each movement type with 7 iterations, resulting in 42 runs per participant. And yeah, for each block, we then conducted the questionnaires. We had 15 participants, 6 were female, aged between 18 and 35 years, and none of them suffered from color vision impairments, and all had corrected to normal or normal vision, where we also made sure that nobody was wearing glasses because we wanted to avoid any effects there too. So from the results, what we see is that we finally were able to show that IC360 is beatable, especially when it comes to moving out of view objects. You see that 3D radar outperforms IC360 in for all 3 movement types. Especially interesting is here the high value for the distance movement for IC360. Which is, we think it's due to the case, or we saw it in the results that do like an IC360 distance is encoded with color. So close red, far away blue, and it's a color gradient in between these 2. Some people mixed that up. So when like a movement was coming towards the user, they were mixing up the colors and thinking it was like going away instead. So they draw like a 180-degree wrong vector here, and that lead to like the higher error here for this specific case. Yeah. What did we learn from our findings? First of all, Focus+context does not have the ability to keep the proportions of 3D space. So as we saw, like IC6 is just an example, but when we want to like show things in context, we need to like bring them to the user's field of view, and thereby we lose like the ability or like the understanding of the 3D space. In IC360 specifically by splitting it up in 2D position and color, but also with like the compression of the information along the borders of the screen. Overview+detail, but has like disadvantages when it comes to quickly locating those objects out of view. So because like in IC360, when a dot is presented to the right, I know I have to just look to the right side to find that object. While for 3D radar, I first have to like look at the radar, see where I am, where the object are, and then where the object is in relation to me, and then I can like turn around, which like results in slightly worse search times here. Also, through the ecological validity of our approach, we evaluated both techniques in a simple ground and sky scene. with just one moving object at a time. We think that is a suitable approach to gather first insights. But now that we understood these differences in both techniques, we should look into different application scenarios because we think they have a huge impact on the performance of users, especially also on the workload. And therefore, we should also look into workload in the future. Yeah, what did we show here? We compared two visualization approaches, Overview+detail versus Focus+context. We saw in the end that 3D radar for moving objects out of view objectively and subjectively worked best. We had, in the end, 13 out of 15 participants who said they preferred 3D radar over ICC60. And the system usability scores also show that that 3D radar is more suited for this, and people already felt that their performance was not that well, and therefore thought that the visualization technique itself wasn't that good, and therefore rated this was just 48 on the system usability scale, while in the original paper we had way higher scores for the system usability scale here. Sorry. So what can we say? ICC60 is better for quickly locating out-of-view objects, and 3D radar also can encode more information. So because of the overview-of-detail approach, we can also encode, for example, the orientation of objects out of view or their size, which is all not possible because we lose these abilities in Focus+context approaches. And with that, I would like to thank you for your attention.
Perfect. So thank you, Uwe, for your presentation. Questions are ready.
Yes. Thank you for the talk. So I have a little bit of a clarification question about the angular field of view of the objects and their velocity. It's a little bit hard to grasp the scale of how fast they were moving and how big they were. Can you talk a little bit more in detail about that?
Yeah, the size doesn't matter because we think about where is an object located, so how big it is not conveyed here. So what we convey is direction and distance towards that object. That's the first thing. And the speed, so this is explained a little bit better in the paper than I could do it here. We created a sphere around the user of 10 meters. And every object was moving 5 seconds and 8 meters in distance. So we made 8 meters in 5 seconds. That's the speed of the objects we draw here.
Okay, and just a quick follow-up. So when they actually turned to find the object, did you also measure the time in which it was in their binocular field of view, or was that not counted?
So the task here, maybe I didn't explain that too well here. So the task was that participants were not seeing these objects. So basically they were shown out of view in the visualization technique, and then the users used their controller to draw where they thought the object was moving around.
I see. Okay, thank you.
Hi, very interesting talk. Thank you very much. If I understand correctly, that the IC360 technique is very much like what Xiao and Benko from Microsoft did in the sparse peripheral displays. And what I wanted to ask is, how do you think this technique can perform in augmented reality with limited field of view?
So first of all, the paper you mentioned from Kai 2016 is augmenting field of view from Xiao and Benko, I guess. They have LEDs around. Yeah, but what they were doing is just extending the field of view. So the field of view of the AR device, for example, is 90 degrees, and then they extended it farther with LEDs, which means objects in that part would be shown by the LEDs, but behind the user would not be visible in that kind of technique.
So you did it for VR headset, but I am asking about AR and your technique. And what I was saying is that your technique is like theirs, but virtual.
Yeah, yes. So in AR, we have in the original paper, we tested IC60 in AR. And we used Google Cardboard for that, with roughly 45 degrees field of view. and the results were similar, comparable to like the results here. When we tested it on HoloLens, for example, it was a little bit worse because the HoloLens has that much limited field of view that this radar adds a lot of clutter to the screen, so people were perceiving less good there. But we have evaluations on that also in other papers.
Great. Thank you very much.
Okay, so I have one last question. We are still in time, so it's fine. Did you get from questionnaire or from quantitative data some insight to redesign the interfaces, or just, I mean, thoughts for try to redesign completely the interface, or mixing or morphing something?
Yeah, so participants were suggesting different ideas. For example, that we could bring this 3D aspect to like IC360 with, like, for example, these proxies coming closer or going farther away. We also did already like a little pilot testing on that, and they were actually performing worse because still the proportions of the 3D space are still presented differently. Therefore, it's mixing up our understanding of like how objects move out of view. So it's really hard and tricky.
Okay, let's thank again our speaker.